So hello everyone, welcome to the discussion section. Yesterday during the lecture, we introduced the dual bounds and duality for IP programming. During this discussion, I was planning at least to remind you what duality for linear programming was, and also give you some examples about solve some examples from the book about the dual bounds. First of all, is anyone who would mind me to go over the LP duality? Probably you know it perfectly, and so no objections. Okay, cool. Right. Something wrong with that? Probably just show this. Okay, so the dual bounds. Sorry. Do I not have that duality slides here? Okay. So let me start with LP duality specifically. There are like LPs can be written in multiple forms. Here you can see the inequality form that is that had like all of the constraints in the problem are consist of inequalities. There is a standard form where you have a non-negativity constraints for variables, which are coupled with linear equality constraints for general linear functions. And there is also a symmetric form where all of the inequalities are inequality constraints, just like in inequality form, but all of the participating variables are assumed to be non-negative. So basically, symmetric form is a special case of inequality form. However, all of any linear programming problem has a symmetric form. It's pretty easy to verify this by just going over the LP the LP equivalent transformations. By applying this transformation to any form, to any LP, really, that doesn't have to be in any form. You can convert it to an LP in one of this main forms. Let's go over this transformations quickly. The first property, that maximization is a negation of a minimization of a negation. This is a property that you already know. Then you can multiply inequalities by -1 to switch the sign. You can decompose an inequality constraint into a couple of inequalities. If you have an inequality constraint, you can introduce a slack variable. This is going to be non-negative, and convert an equality constraint into a couple of the non-negativity constraint as I greater than or equal than 0, and an equality constraint with the slack variable. You'll have seen this, right? Cool. The same thing is possible to do with the inequality constraint in the other way. And then if you have a free variable that is not constrained, is not bounded by anything, like you don't have a non-negativity constraint for xj, you can always decouple it into a couple of variables, xj plus and xj minus, such that both of them are greater than or equal than 0, and then you will end up with 3 constraints, 2 non-negativity constraints, and 1 equality constraint. And therefore, even if you have a free variable, we can always boil it down to a linear programming symmetric form. If you have a problem in symmetric form, or really like the same thing can be delivered for any kind of form of an LP program, but specifically if you have converted your problem to symmetric form, there are 4 types of certificates you might be interested in. First of all, you might be interested to certify that the problem is feasible. You might be interested to certify that the problem is bounded, or it is infeasible, or it is unbounded. For each of these cases, you can come up with the certificates in the form of vectors. The feasibility certificate is just a feasible solution for a problem. So you just take constraints in the problem and find a problem point that satisfies them. For boundedness constraint, you just aim to okay. So let's first do with with the direction of unboundedness. The direction of unboundedness is still in the same space as the original problem. So it is kind of a point in the same space. Doesn't have to be a feasible though. What we require from a direction of unboundedness is that it has a negative correlation with the coefficient Cj, with the vector of coefficient C, and also it, like, when we scale the vector Z, it doesn't have to be bounded by the vector B. So basically the same system of inequalities has to be satisfied, but we substitute the zeros instead of B. And the certificates of invisibility and boundedness are vectors in a dual space. So it's a space that that is dual with respect to the matrix A, the matrix of the inequalities, and basically it is a feasible solution to the dual problem, and also a certificate of unboundedness for the dual problem as well. So these are the LP certificates, and the duality theory is telling us that if we have found a point, like a couple of points X and Y, one is primal feasible, the other is the dual feasible, and also there is, like, basically the objective functions for the primal and the dual problems for this couple of the points are equal to each other, then we have found an optimal solution to the LP problem. The tightness constraint, tightness condition can be substituted by the complementary tightness condition. So these are the certificates for LP that we were talking about during the lecture. They are very useful for our purposes when we are talking about relaxations, LP relaxations of integer programming problems. So this is the duality theory, the primal and the dual, how we can convert a primal in symmetric form into a dual in symmetric form. Sorry, in a symmetric form. And if you are having a problem that is not in symmetric form, you still can convert it to dual by utilizing the table here. So if you have a constraint of like with one of the types in an inequality or inequality constraint, you introduce a corresponding decision variable that will have a constraint of its own, or it will be free in the dual problem. On the other hand, if you have a decision variable that is constrained, for example, it has a non-negativity constraint or a non-positivity constraint, in the dual problem it will convert, and it will be converted into a constraint on like on the domain of the dual problem itself. This provides you with quite a quick and easiest way to formulate dual problems, LPs to the dual problems. I'm showing you to you just because you have problems in your problem set that requires you to construct duals to LP relaxations. So if you have any questions regarding how to do this, I can give you a couple of examples on how to construct LP duals. But it is on the website already uploaded. So if you want to come back to it, feel free to do it. Any questions regarding LP duality and everything? No? Okay, cool. Then let's switch to the next topic, which is the dual bounds. Okay. The first problem that we're going to be discussing concerns the maximum cardinality matching and the minimum cardinality covering that we have covered during the lecture. This problem asks us to find the maximum cardinality matching the graph over here by extraction, and then give a proof that the solution is optimal. It is not that difficult to find the matching. Moreover, it looks like there are multiple maximal matchings, but one of them is claimed to be this one. The first edge is 2 dash, and then 3 1 dash, 4 3 dash, 5 dash, and 6 dash. It is kind of easier to deal with this particular example, even though there are multiple nodes and multiple edges, just because it's a bipartite graph. We have two sets of nodes that are not like the nodes in each set are not connected to each other. So it is kind of an easy problem even from the computational viewpoint. How to show that the matching that we have found is in fact an optimal matching? Well, you probably remember from the lecture that if we have found a relaxation, a dual bound, if we have found a dual bound that matches the value of our feasible solution, then our feasible solution is in fact the optimal solution, right? So everything that we need to do is to find, like we also have proven that covering is the dual problem for a matching, and therefore we are it would be sufficient to find a covering such that it also consists of 5 entries, and such covering does exist. It's the covering 2, 3, 6, 2, 3, 6, 3 dash, and 5 dash. It's quite straightforward by just by verifying which, like, for each edge that it is until in fact it is a covering, and it does consist of 5 nodes. Therefore, the cardinality of the space of our matching and the cardinality of our covering coincide, and therefore we have proven that the solution that we have found is in fact optimal. Any questions regarding this problem? None? Great. The next problem is the problem 297 from the book. Eventually, what it asks us to do is to formulate a network formulation, come up with a network formulation for an integer knapsack problem. But we're gonna be doing it in several steps, just because we can do it, and these steps will require us to, like, our understanding of the problem of the method of constructing duals and proving that they are duals. So we are dealing with the problem in the form on the top. You have a maximization problem of linear programming problem with a single constraint and the variables belonging to the set of integer vectors. We, like, all of our positive, like all of our coefficients are in fact positive, AJs and Bs and the B, and they are all integer. We are introducing a function G, or you can think of it as a vector actually, just because we are just putting our index in the parentheses here. So it really just consists of B numbers. It's just B numbers, because D will go from 0 to B. So G of D is going to be the result of maximization of the same linear objective with the same constraint. Only on the right hand side we have substituted the D instead of the B. So we have changed the capacity of our backpack that we are using, and the corresponding problem of maximization will be done with P of D. Okay. Any questions regarding the notation? We are just introducing new problems that vary the the capacity of our bag. The first subproblem is asking us to show that like the two inequalities. The first inequality is that the g of d is greater than or equal than g of d minus aj plus cj. Let's take a look at how that can be done. Let x star be the optimal solution to the problem p of d minus aj. So instead of d, we substitute d minus aj. And the optimal objective value for this problem is cx star. Therefore, we have the following inequality called because x star is a feasible solution for our problem. Then, if we consider x star plus ej, where ej is a vector of all zeros and one at the jth location, jth component, this vector is going to be feasible in P of D with the value cx star plus cj, just because we basically what we are having, we are just adding a new item, the item j, to our backpack, just because when we go from d minus aj to d, we kind of add enough capacity in order to add this new item j. Therefore, g of d is going to be greater than or equal than cx star plus cj, which is, since cx star is in fact our g of d minus aj, we can substitute it and we'll get that g of d is greater than or equal than g of d minus aj plus cj. So we have proven the first inequality. Any questions regarding the first inequality? Sounds good. Let's turn to the second inequality. G of d is greater than or equal than g of d minus 1. This one is really very similar, just because we can again assume that x star is the optimal solution for p of d minus 1, with g of d minus 1 is equal to cx star. And we are saying here that ax star is less than or equal than d minus 1, just because x star is the feasible solution for p of d minus 1. Then x star is going to be a feasible solution for p of d with the value cx star, just because it is like, since this inequality holds, if we cross out this minus 1, this inequality also must hold. So cx star must be a feasible solution, and therefore g of d is greater than or equal than g of d minus 1. This for now it kind of looks artificial, but this two inequalities gonna play a role in our further construction. Any questions regarding the proof? Okay, no questions. Now we aim at showing that this problem here is in fact a strong dual to the knapsack problem that we have had on the first slide, with the b in the constraint. Let's take a look at this problem here. So we are minimizing over all of vectors y. I just remind you that y is a vector of b variables, of b numbers. We are minimizing over all of the vectors y, with the first inequality being the exact same inequality as we had for g, and the second inequality being the exact same inequality that we have just proven for g. We just pushed the d minus aj and d minus 1 to the left hand side, and y of 0 is equal to 0 is in fact true for g of d. Just because if you put 0 on the right hand side, and all of the aj's are greater than 0, then it's obvious that the only feasible solution is going to be 0. So we need to take this problem now and show that it is a dual. First of all, it is a dual, and then we need to show that it is a strong dual for the original solution of the integer knapsack problem. Let's start by showing that it is in fact a dual. So suppose that there is a y such that y of b is less than g of b. We know that g of b is the optimal solution for the original knapsack problem. So if this is not a dual, then there must be y such that this inequality holds. And x, like we assume that the x, or like the same thing that used to be x star is now x. X is the optimal for P of B for the original knapsack problem. We can use the fact that y of b minus ax. This is just the summation from the above. Y of b minus ax is greater than or equal than cx. Do you like? Does anyone can anyone tell me how to prove this inequality over here on the top? We only have that if we subtract aj, then we will get greater than or equal than cj. How can we go from this inequality to? Any ideas? No ideas? Sorry, say it again.
So is it like, is A just like a matrix and it's just like for all x, it's like the sum in a way?
Yeah, so actually, like ax, I just used shorthand notation. So A here is not even the matrix. You can think about it as a matrix, but it's really just a vector. So ax is just A transpose x, right? It's just it's just a number. X is telling us x is a vector, and it's telling us how many items we have put in our bag. Like there might be like three for the first item, 4 for the second item, 0 for the third item, and so on. Basically, this thing is like this value here. On the one hand, it is the capacity that we have used in our backpack. On the other hand, we can take a look at this inequality up above and write down the following thing. Y of b, like let's say that the first item we have taken 3 times. Y of b minus y of b minus a1 is greater than or equal than c1. Then y of b minus a1 minus y of b minus a1 is greater than or equal than c1 again. This thing is just 2a1, and if we sum these two things up, we will get an inequality y of b minus y of b minus a1 plus y of b minus a1 minus y of b minus 2a1 greater than or equal than 2c1. Greater than or equal than 2c1. And we can see that these two things actually destroy each other, and we end up with y of b minus y of b minus 2a1 greater than or equal than 2c1. And then we can continue doing that. We can do this once again for a1, and then we can start doing the same procedure for c2, and so like for the second and for the third variables, and eventually by doing this we will get to the inequality of this one, that y of b minus y of b minus a transpose x is greater than or equal than c transpose x. Sounds good? Any questions? I can actually explain this once again if it's not clear.
Yeah, could you do that? Just I'm having a hard time figuring out how you get the x, or like how you get from what you were doing in the beginning to you get the x term.
So once again, you're saying that like is this step is this step?
I understand that stuff, but I just didn't understand how you got like how at the end you get b minus that. Yeah.
Okay.
Yeah.
So let me then write this down more explicitly. Let's say that our x is this thing 2, 3, 1, and and our A consists of three values: A1, A2, A3. Then A transpose X is 2A1 plus 3A2 plus A1, A3. We have already obtained this inequality that y of b minus a1 minus 2a1 is greater than or equal than 2c1. Now let's get from this inequality to the inequality of the therefore our inequality, like our this form, is going to be for this specific case is going to be y of b minus y of b minus 2a1 plus 3a2 plus 1a3. And this thing is already something that we have obtained. Now we would like to add these things and these things to our mesh. So what we do is we say we write down the inequality y of b minus 2a1 minus y of b minus 2a1 minus a2 is greater than or equal than c2. And now we take this inequality here and this inequality up here, and we add them up. And what we get is y of b minus y of b minus 2a1 minus a minus a2 is greater than or equal than 2c1 plus c2. So you can see that the more terms I'm adding here, the more terms appear over here. And if I continue doing this, I will eventually get to here, and this is just a different expression of saying that.
Yeah. Okay.
Sounds good. Okay. Awesome. So we have obtained this inequality over here. And we remember that Cx was actually g of b by definition, just because g of b is the optimal objective, the optimal objective value, and therefore we can say that. And also we need to notice that y is actually a non-negative vector, just because y of 0 is equal to 0. And y of 1 is also going to be greater than or equal than 0. And y of 2, therefore, are also going to be greater than or equal than 0. So this thing over here is, in fact, non-negative. And so we can just drop it, and our inequality will still hold. Therefore, y of b is greater than or equal than g of b, as y is greater than, like for any y that is feasible for this problem. Therefore, we have came to a contradiction. Why our y of b cannot be less than g of b, and therefore this problem is in fact a dual for the knapsack problem. Now we need to show that it is a strong dual. We can just take y of d being equal to g of d, and by the first point, by the first sub problem, we know that both of these inequalities hold for g of d, and therefore it is in fact an like the tied bound holds. Therefore it is a strong dual. Any questions regarding showing strong duality for this question? Cool. Awesome. Part 3 is asking us. So now notice that there are no integrality constraints for this problem. This problem is in fact a linear programming problem. We are taking the, okay, so now we have a linear programming problem, and we are asked to take the dual of this linear programming problem and interpret the variables and constraints of the resulting LP. The dual is basically by proceeding the way I have shown you before about the taking the duals of linear programming problems. We can write down the dual as following, where our constraints are x, jd, and zd. We have also two constraints that are making sure. Okay, so let us take a look at the interpretation and then see how it happens to be. You can imagine yourself a graph consisting of b different nodes, actually b plus 1 because there is a 0. Basically, as we are getting more and more of items in our backpack, we can imagine that we are jumping into a new node. We start from node 0, and then, for example, we have taken the first item that weights 2, like the value of 2. Then we have jumped into the node 2 right away from 0. And our aim is to end up in the node B by maximizing the total weight of all arcs that we have gone over. This is in fact the interpretation of the problem on the top. So this is this problem is called the longest path problem, because we can interpret this as like the weights of the edges in the graph as the length of the path, and we are trying to maximize it. So this is the longest path problem in an acyclic graph with the nodes from 0 to B, where xjd is responsible for the arc from d minus ag to aj to d. So this is basically the fact that we are jumping from a node d, like for example 2 kilograms ahead, to nodes ahead. And zd, we are assigning zd to 1 if we have used the arc d minus 1d. Basically, the arc d minus 1d does not add us any value to our backpack. It just means that we are disposing of some space. We're never gonna use it. We will talk in more details about longest path, because this is one of the integer programming problems that can be solved to global optimality. However, like in this particular formulation, it's not even an integer programming problem. So I just want to point out that we have gone from the knapsack formulation to this interesting longest path reformulation by taking dual twice. We have taken a dual over here, and then we took a dual of a dual, and dual of a dual just because both times when we were transferring from one dual to another, we were transferring to a strong dual. The first one was a strong dual because we proved it. The second was the strong dual just because it's linear programming dual, and duals for linear programming are always strong. Therefore, the eventual problem is in fact an equivalent problem to the one that we have had before. In general, this is one of the main ways to show that two problems are equivalent. You just take dual over dual. Cool. We still have some time. Let's take a look at the problem 299. Suppose that the value function phi of d, which is the maximization objective of an integer programming problem with the right-hand side in the inequality constraints equal to d. is a finite value for all d for all integral vectors d. We need to do two things: show that the value function phi is superadditive, and then we need to prove the theorem that we have, like, about the strong duality that we have seen during the lecture, if you remember the last theorem about superadditivity. So basically, this problem asks us to prove that problem, to prove that theorem. First of all, we need to show that the function phi is in fact superadditive. First thing that we notice is that phi of 0 is greater than or equal than 0, just because 0, like putting x being equal to 0 into that constraint satisfies it. If right hand side is equal to 0, and therefore, since it is a feasible solution, the optimal solution cannot be less than that. Therefore, phi of 0 is greater than or equal than 0. Moreover, if you assume that phi of 0 is greater than 0, then nothing actually stops you. So let's say that you have found an x that gives you a positive objective value, even if d is equal to 0, and it's just feasible for d is being equal to 0. Nothing stops you from multiplying that x by 100, right? Or by 1,000, and the objective function is going to grow. Therefore, if phi of 0 is greater than 0, then phi d is going to be unbounded, which is a contradiction for like to our assumption that it is finite valid for all d. Thus, we have proven that phi of 0 is equal to 0. Now, suppose that there are in fact two different vectors, d1 and d2, and suppose that phi of d basically there are two optimal solutions for the problem for both of these vectors d. The first solution is denoted with x1. The second solution is denoted with x2. Therefore, the optimal solution, the optimal objective values are going to be cx1 and cx2. And since our x1 and x2 are optimal, they must be feasible. Therefore, the inequalities must be satisfied for both of them. We can consider x1 plus x2, and that x1 plus x2. If we just substituted, so if we just add together these two inequalities, we will get that a times x1 plus x2 is less than or equal than d1 plus d2, and x1 plus x2 is in fact also an integral point. Therefore, x1 plus x2 is going to be a feasible solution for a problem where right hand side is d1 plus d2. Moreover, it is a feasible problem. It is a feasible solution, and it has objective value of c of x1 plus x2. It follows that phi of d1 plus d2 is greater than or equal than c of x1 plus x2, just because we know that it is feasible and it is a value, which is equal to f of d1 plus f of phi of d2, and therefore, and this inequality here is the inequality that we need to show in order to prove that something is super additive. So we are done with showing that phi is super additive. Any questions regarding this proof? Okay. Now we need to use a similar technique in order to show that phi is non-decreasing. Just because we remember that in our theorem we were optimizing over super additive and non-decreasing functions. So let's assume that d1 and d2 are actually comparable vectors, and d1 is less than or equal than d2. And x1 is feasible for then x1. If x1 is actually feasible for the problem defined with d1, then it is feasible for the problem defined with d2, just because we know that vector d is greater. So it's like if it satisfied the inequalities for a smaller vector, then it must satisfy the inequalities for the bigger vector. And therefore, we have shown that phi of d1 is less than or equal to phi of d2. So therefore, phi is in fact a super additive and non-decreasing function. Now, let's remember what the theorem was saying. The theorem was saying that provided that it is feasible and its linear programming relaxation has a finite optimal value, the integer programming problem, the one that we were just considering, its optimal value is in fact equal to the optimal value of optimization over the space of non-decreasing super additive functions. And our aim right now is to prove this equality. In fact, it is just one line of proof. It is just enough to say to make sure that phi is in fact a feasible value for both the primal and the dual problem, just because it satisfies the inequality it needs to satisfy. So you would still need to show that the problem on the right is in fact a dual problem, but it is kind of a more of a trick question. So we are here we assume known that the problem on the right is in fact dual, and we have just shown that it is in fact a strong dual, if it is dual at all. But it is a good exercise to show that the problem on the right is dual at all. Okay. Any questions regarding the problem 299? No questions? Cool. Then we have the Lagrangian relaxations and its strength. So I have touched on this during the lecture. I would like to remind you that there is a statement we have seen a theorem that was saying that the value of the Lagrangian relaxation that is defined by this equation, minimization over all non-negative u, which are the vectors of Lagrangian coefficients of the z of u, the Lagrangian relaxation expression. So the minimization, this minimization or this Lagrangian dual is in fact equal to the maximization of the original function over the dualized inequalities and x belonging to the convex hull of the original of the non-dualized domain. This statement can be shown. It's done in the book, so I will probably not spend much time on this. I would like to solve with you the problem 1076, which is about the strength of Lagrangian dual. So we have a Lagrangian decomposition formulation. We are considering a problem consisting of a minimization of a maximization of objective of a linear function and two sets of linear inequalities. One is denoted with a1x less than or equal than b1, and the other one is a2x is less than or equal than b2. And we have all of our variables to be integer. The reformulation of that problem is given over here. It's the exact reformulation. We just assume we instead of the vector x, we introduce two vectors x1 and x2, which actually have to be equal to each other because x1 minus x2 is equal to 0. And then we decompose our objective function into two parts with the coefficient alpha, which obviously just because x1 is equal to x2, it is just the same objective function. However, we separate the system of linear inequalities into two, into each group of systems of linear inequalities. We substitute a different value of x. We consider the Lagrangian dual of this formulation, which in which the n constraints of equality constraints are dualized. What is the strength of this dual? Any questions regarding the formulation? What we want to do? We just want to dualize this constraint. That's a long story short. Sounds good. So first thing that we might ask is that, well, these are equality constraints, and we were introducing Lagrangian relaxations and dual for inequality constraints. For that, I can say that we can represent equality constraints as inequality both ways, and what we will end up with is basically the same thing, but this vector u is going to be free. It's not going to be constrained. So it's pretty easy to check. You can take it home as an exercise. That if you do this decomposition into two, and then you introduce two sets of Lagrangian variables, and like you will end up with the fact that these two sets actually correspond to each other, and you can you will have something like u minus plus u minus, sorry, you will have u plus minus u minus, and both of these variables are greater than or equal than zero, greater than or equal than zero, and then you can just introduce u, which are free variables. We'll probably do this anyway. So the solution to this problem is the following. We consider the following two problems, L1 and L2 of u, where we maximize over the x. In the first problem, we maximize over the x1. In the second problem, we maximize over the x2. And we consider L of u, the relaxation of the original problem, as a sum of L1 of u plus L2 of u. And the statement here is that the relaxation of the original problem is in fact a minimization over L of u. Why is that the case? If you just aim at dualizing this problem, you would have a decomposed objective function into summation of two functions, and you would have two sets of inequalities which are independent of each other, and maximization over maximization over f1 plus f2, f1 of x1 and f2 of x2 over x1 belonging to x1 and x2 belonging to capital X2. This problem can be decomposed the same as maximization of f1 of x1 over x1 belonging to capital X1 plus maximization over x2, f2 of x2 and x2 belonging to capital X2. Just because our sets, our domains are independent, completely independent, we can substitute. We can take the optimal value for this problem and the optimal value for this problem. Substitute these two values into this problem, and our eventual solution and eventual value are going to be exactly the same as the sum of these two. Okay, and so we can do this here. We can substitute that. We can do this decomposition and substitute it, and our eventual thing is going to be exactly the same as the Lagrangian dual to the original problem. And then we just apply the theorem 10.1 about the convexification of the domain. What we will end up with is an expression that tells us that we are maximizing over this big linear function over a convex set, over a convex hull of one of the first set, and the convex hull of the second set. And therefore, our strength of the Lagrangian relaxation is the intersection of the two convex halves of the two sets. The first one consists of contains the first system of linear inequalities, and the second one contains the second system of linear inequalities. So this is called the strength of the dual. Thank you very much for your attention. I'll see you on Thursday. Please let me know if you need to. So I will be here for now until I'll be kicked out. If you have any questions. Sounds good. Thank you.
Will you post these slides?
They are posted. Yeah. They are on my website. You just go to my website. Yeah.